This problem is again another combination of bearing and shearing stress. So they usually appear, no? If we have joints or lap joints, or like this, so joining two plates. So you have here plate A and B, each 100 mm. I think it's 110. Let me check. It's 110 mm. So it's actually 110 mm wide. So both plates A and B are 110 mm wide. The bolt diameter is 20 mm. We're given with the limiting shearing stress of the rivet 60 megapascals, and we have the bearing stress of the plate, which is 120 megapascals. So we have P here acting on both sides as tensile forces, and then we're asked to find the thickness of the plate and the largest average normal stress for the plate, no, or for the joint. So solution. So our working equations, we have tau equals V over A, and then we have stress, bearing stress just equal to PB over AB. So in order to find the thickness of the plate, we'll have to make use of this one. But in order to find the force that we need, the PB, you have to get the shear force, no, or the P, using the given shearing stress of the rivet, no? So using the shearing stress of the rivet, you have V equals A, and then you have 60 MPa, which is Newton per mm square. Then you have pi over 4 times the given diameter is 20 square. That's mm square. This cancels out. V is now equal to 6,000 pi Newton, no? Which is also essentially just equal to P, and the same PB. Okay, because if you cut section right here and you go summation of forces along the x-axis, you only have P and V. So V equals P. You also only have, and then for the plate, it's only a single force pulling the plate. So the internal force in the plate, within the plate, also equal to P. No, there are no other forces acting on the joint but P. So now that we have PB, we can solve for the thickness of the plate. So we have AB, which is equal to, we have PB divided by stress P. So we have PB is 6,000 pi Newton divided by your stress B, which is 120 Newton per mm square, and then the area is just equal to, the bearing area is just equal to dt, which is diameter 20 mm times t. So you may wondering why, you know, why it's dt. So again, if we look at this in isometric view example, no? So we have just a quick drawing, and you have, so if we have a force P pulling to that direction, then you have the bolt here. So if we have P here pulling to this direction, we will have a reactive force here pushing the bolt, because the bolt will have to resist this particular area, and then it will push this area of the plate. Okay, this area of the plate. So the dimension of this area is just this one is D, and this one is we have the T. So this area is your bearing area, because it is what is the area that's been pushed by a resistive force or reaction force due to your external force. So again, if you can imagine, if we pull this plate that direction, this bolt somehow pushes this particular area here of your plate. So that's why it's subjected to your bearing stress, because again we say that the bearing stress is the contact pressure between two separate members. So here now is your separate member, the bolt and the plate. So as you pull this plate, the bolt pushes to this area, which is just equal to this area, no? So this is area has been the bearing area, 20D, which is the diameter times the thickness, just diameter times the thickness. So T now is just equal to 7.85 millimeters. So now you have your first requirement. The second is the largest tensile stress, the largest average tensile stress in the plates. So again, now we analyze the plate. So this is for letter B. So if we analyze this plate, example, you have a hole here, bolt. This is plate A, and this one is 110 mm. So imagine if you have a piece of paper. If this is a piece of paper and you're applying a force, tensile force to both directions. So if you're pulling the paper, for example, the section, the most vulnerable section is this section where there is a hole. So technically this will have a much lower strength compared to this section. So this section will fail first compared to this section with no with complete length. So we will analyze this section for the largest average tensile stress. So we have the equation for stress, just P over A. So you have P equals 6,000 pi Newton. Area is just 110 minus the diameter, which is 20 mm, times your thickness, which is 7.85 mm. So Newton per mm squared, just megapascals, equals 26.67 megapascals. So again, this can be carried by this particular section. So because if you use this section, you will not have a reduction, therefore you will have a much lower you have a much bigger stress, so that can be carried by this one. So we will use this one, which is safe for both the section with the hole and section without your 20 mm diameter hole. So again, this section is more vulnerable compared to this section. So it's more likely that this will fail first compared to the section with complete width. So that's your answers. Thickness and the largest tensile stress for the plates.